Okay, the last talk is given by Joseph Inosset. The title is Projective Toric Designs, Quantum State Designs, and Mutual Unbiased Basis. Please start.
Thanks everyone for coming. So today I'll tell you about this work with these four people. I think one of them is in the audience. So this is the summary of the talk. In fact, I really could just leave this slide up the whole time and not really show any other slides. But this is, I guess, the takeaway that I'd like you to take is just there's various objects in quantum information theory and mathematics that seem to all be connected in this weird way to these projective toric designs. So I'll show this slide again at the end, and hopefully all the various boxes will be a little bit more clear. This is the brief overview. I'll start by definitions, and then section 2 is going to be a little bit dry, unfortunately. It's just mostly talking about projective toric designs, which I haven't yet told you. I won't really tell you why to care about them until section 3, so hopefully it's not too dry. But section 3 and section 4, I think, are the sort of main points. And then actually, the thing that I'd like to spend the most time on is really just section 5. Which is open questions. So let me define a T-design. For those, we had a bunch of talks this morning about unitary T-designs. Let me just give a quick definition so everyone's on the same page. Very generally speaking, I need some measure space M and then some set of polynomials. In general, you can have any set of functions with some filtration, but usually you just deal with a set of polynomials. Then a T-design on this measure space is just some weighted set, so that when you average over this weighted set, that average is equal to if you were to integrate over the full space whenever you're dealing with polynomials of degree T or less. So T really characterizes the strength of the design and how well the design matches integration over the full space. So various examples that show up in quantum information theory for spaces that you would like to have a design on. So unitary and projective unitary designs are sort of the talks from this morning. This talk is going to be mostly about, bottom here, projective toric designs and projective toric designs. Actually, QIP 2 years ago in Ghent, we talked about the bottom left. These are designs on the space of temperate distributions. And these are also related to projective toric designs, but I won't actually discuss that at all here. So let me define the projective torus. I'm going to define the normal torus as just the diagonal subgroup of the unitary group. So this is the maximal torus of the unitary group. And then the projective torus, I'm just going to mod out by a factor of U1. So U1 acting globally. So these are just like take e to the I theta and put it in a diagonal n by n unitary with all the thetas equal. So then sort of following the previous slide, a set is a projective toric T design if this condition is satisfied. So let me just put this back to back with the sort of standard definition of a unitary T design, which really I think it might be better to call these projective unitary T designs, but in any case. So the bottom here is a unitary T design, and the top is a projective toric design. And the difference is just that on the right-hand side, you're integrating only over the maximal torus of the unitary group, not the full unitary group. So the dry section, bounds and constructions. So mostly this will be some definitions and some results, but they'll be useful for later. So let's start off by discussing the root lattice of the projective unitary group. So this is A sub n minus 1. And the intuition here, I won't give too much intuition, but the root lattice of Pu of n really tells you something about the polynomial structure on the projective torus. The number of points on this root lattice that are at most a distance s away from the origin, these are called the crystal ball numbers of a lattice. This is a well-defined number for any root lattice, and there's sort of interesting sequences. So there's this work by Conway and Sloan from 1997, and they give a closed form solution for these crystal ball numbers. And it takes this form. This is some hypergeometric function, which obviously can be written as some sort of sum as well, but yeah. So this, using this, again, I haven't described the connection too clear, but the fact that these root lattices are really characterized monomials on the projective torus, you can then prove this lower bound on the size of these projective toric T designs, sorry. And that is given here. It's just given by this crystal ball sequence. And furthermore, we find, which I'll actually show this a little bit later, this bound is saturable for t equals 2, so projective toric T designs. We think it's saturable for any even t. So yeah, like I said, this theorem will sort of be used later. Now let me start with one of the other boxes on that picture I showed earlier. I want to show the connection to additive combinatorics. So one of the objects that people care about in additive combinatorics are called difference sets. And in particular, there's a type of set called a BT mod M set of size n, which is kind of a mouthful. And it's just some set of integers such that if you add t of them together and then take their modulo m, then that addition will be unique up to reordering. And so for example, for t equals 2, these are also called Sidon sets, which are sort of notoriously unstructured objects in additive combinatorics. And this condition, the B2 mod M set condition, just reduces to I have some set of n numbers specified by z sub a, for a going from 1 to n, and the pairwise sum of these two numbers needs to be unique unless I just swap the ordering. So what we show is that for any projective toric T design that is isomorphic to a group, then these designs are in one-to-one correspondence with these BT mod M sets, so these difference sets. And the sort of thing to keep in mind here is that finding designs is always hard because they're unstructured. So if you add in some structure, it can help you. And so the structure we're adding here is the group structure. People also do this a lot with unitary designs, for example. So again, this just sort of gives constructions that we'll use later. A design is a group design if it's some subgroup of P of T to the n. This is sort of tangential, but it's sort of interesting. This gives a corollary, given the previous two slides, this gives a corollary on the size of these BT mod M sets. Basically, these sets have to satisfy this particular inequality. And as far as we know, this is not in the additive combinatorics literature, which is kind of neat. I mean, it certainly could be there. We missed it from 100 years ago. But it's kind of neat that it gives you a nice connection, a geometric understanding of these different sets, and it really sort of, in some sense, goes through quantum, which is, I haven't showed the quantum part yet. But so now we'll use these sets to construct projective toric designs. And via a totally different reason, Singer in 1938, he was studying finite projective planes and etc. He constructed these BT mod M sets with these parameters. And this, just given the previous slide, this immediately gives us projective toric T designs of this size for all T for all n. So when T equals 2, again, these are Sidon sets. And Singer's construction actually matches the lower bound that we had for various dimensions, whenever the dimension -1 is a prime power. So so our lower bound is tight in the sense that there are infinitely many dimensions for which we can saturate this lower bound. But we're not sure if it's tight in every dimension. So now the plan is to use these objects that we've discussed and use them for various conjectures and theorems in quantum information theory. So hopefully this is where it gets slightly more exciting. So a complete set of mutually unbiased bases, let me give you the definition and then maybe I'll give a tiny bit of a history. It's really just a set of n+1 orthonormal bases of C to the n, such that if you look between orthonormal bases, the inner product of any two vectors in these bases has this same overlap 1/n. In terms of quantum, the key thing to keep in mind is the uncertainty relation. So it's really telling you that if I measure in one base, if I have these n+1 bases, I can measure in one basis, and it'll tell me nothing about measuring if I were to have measured in the other basis. So for example, for a qubit, I can think of the x basis, and the z basis. This would be a set of two mutually unbiased bases. Because if I measure in the x basis, then it tells me nothing about the z basis. And more broadly, people have thought about these things in continuous variable systems where you have the sort of, a very original uncertainty relation between position and momentum. So the history of these things, it starts actually before this paper that I'm showing, but this is sort of the first paper that really, I think, called them mutually unbiased bases and connected them to quantum information theory. And for me, the reason that they're so interesting is because they're sort of a basic linear algebra problem that people really don't know much about for any dimension which is not a prime power. So for example, the first dimension that's not a prime power is 6. And the sort of existence or non-existence of these things in 6 dimensions is basically completely unknown, which was always sort of captivated me. It's a 6-dimensional linear algebra problem that we just don't really know. So we wanted to sort of find some structure in these complete sets of mutually unbiased bases. And so the first thing we did is to show that a complete set of mutually unbiased bases is actually just equivalent to a subset of the projective torus, so it's just a bunch of points on the projective torus. And that satisfies the following two conditions. One, it just needs to be a toric 2 design, projective toric 2 design of size n squared. And then the second condition is a condition on the sort of like the overlap between any two elements in this design. And so there's this conjecture back in 2015 that basically conjectured that any n-dimensional quantum state 2 design of a certain size must be a complete set of mutually unbiased bases. And the reason that they conjectured this, one reason is because designs are very closely connected to mutually unbiased bases. In fact, any complete set of mutually unbiased bases is a quantum state 2 design. And furthermore, nobody had ever found any designs that didn't satisfy, that weren't also complete set of mutually unbiased bases. So it's a sort of a natural conjecture to make. In our language, because of this sort of theorem with projective toric 2 designs, Jou's conjecture basically states that this condition 1 implies the condition 2. And using the constructions of projective toric designs that I showed on previous slides, we can just explicitly show that this is not true. We can generate many, many counterexamples. And so this sort of immediately disproves Jou's conjecture, which is sort of a shame in some sense, because we would like this nice structure to be connected to these mutually unbiased bases. But in any case, they seem a bit more complicated. And so as I mentioned, already in dimension 6, existence of complete sets of mutually unbiased bases is very much unknown. It was conjectured back in 1999 in Zahner's thesis. He has a various conjectures of this form. And people have sort of been working on it ever since, trying to prove a lot of his conjectures. As far as I know, I don't know if any of them have been proven. However, in prime power dimensions, there are many complete sets of mutually unbiased bases. And in fact, it's sort of interesting to take those constructions and phrase them in the projective toric 2 design language and see the resulting structure. And one of the structures is in this bottom bullet point, which is that all currently known constructions correspond to group projective toric 2 designs. So there's this sort of like, not only are they projective toric designs, they also have this additional group structure. On the other hand, we can prove that in dimension 6, which again is this first dimension where basically nothing is known about these mutually unbiased bases, in dimension 6, the projective toric 2 design cannot be a subgroup. Basically, it's sort of somewhat of an exhaustive search. You can just enumerate all groups in dimension 6. So we conjecture that this theorem is true in general non-prime power dimensions, although we haven't proven it. But in any case, we're sort of happy enough with dimension 6 because this is the dimension that actually has the most attention, because it's a 6-dimensional linear algebra problem. Sort of seems like a homework problem in an undergrad class. It's not, though, so don't give it to anybody. Now let me sort of switch gears and talk about quantum state designs. And these projective toric designs are related to quantum state designs in sort of analogous ways to how they're, or for similar reasons to how they're connected to complete sets of mutually unbiased bases. But what we show is that whenever you have a projective toric 2 design, it yields a quantum state 2 design of size just n plus the size of the projective toric 2 design. And this is actually quite useful. It helps us build lots of families of designs that, as far as we know, have not been constructed before, because we have this nice structure on the projective torus that is not as obvious for quantum states. So let me just recall from the drier slides in the beginning that these projective toric 2 designs, we have constructions of this size for whenever n prime minus 1 is a prime power. So we need, for any dimension, we just need to take some prime power which is larger than that dimension. Sorry, some number such that minus 1 of that is a prime power. And so then using the previous slide, this yields quantum state 2 designs of this particular size. And there's this nice work by Baker et al. Where they basically show that asymptotically, the distance between any number and the next prime number is bounded asymptotically in this way, bounded by n plus, the distance is n to the 0.525. And so what you can do then is just plug this bound into the second bullet, and then you find that we've constructed quantum state 2 designs of size exactly n squared, plus this other factor, n to the 1.525. And this is the smallest known family of quantum state 2 designs. It's asymptotically tight in the sense that there's no coefficient in front of n squared. It's exactly n squared. And we know that the smallest possible quantum state 2 design is exactly n squared. And this relates to another very long open conjecture about SIG POVMs, which are just one way of defining a SIG POVM is just a minimal quantum state 2 design. So I wanted to point out that this construction of these asymptotically tight quantum state 2 designs, this actually came from Jasper and Mixon in January. They did a different, very different proof, and but it's sort of, again, going with the theme of this talk, projective toric 2 designs and T designs in general just sort of connect to a lot of things and actually make this proof quite simpler. It sort of just falls out given all the previous constructions. And yeah, again, it's sort of open as to whether or not these are actually, how related these are to SIG POVMs. They're related in the sense that, projective toric designs can be used to construct these asymptotically tight quantum state 2 designs. But of course, they're not actually tight 2 designs. The smallest you can get with this is n squared plus 1 in certain dimensions. And so it's not exactly clear how closely projective toric 2 designs are related to SIG POVMs. So in summary, we basically studied the sort of theory of these projective toric 2 designs. We disproved this conjecture on the structure of these designs and their relationship to complete sets of mutually unbiased bases. We proved a sort of fundamental distinction between complete sets of mutually unbiased bases in prime power versus non-prime power dimension, and that relates to the group or non-group structure of the corresponding projective toric 2 design. And that's my co-author, and this is the summary again. So hopefully some of these words are slightly more, make more sense, the connection. I didn't go through all of these, and I think there's actually a few more, but I'm happy to talk to anybody afterward. So open questions. So one sort of nice conjecture. So this theorem I showed previously, that in dimension 6, these projective toric 2 designs, if they correspond to a complete set of mutually unbiased bases, then they can't be a group. On the other hand, as I said, all currently known constructions are groups. And so this leads to a natural conjecture. Basically, we conjecture that in any dimension, a complete set of mutually unbiased bases must come from a group projective toric 2 design. So a few things to point out. One, if this conjecture is true, then via the theorem on the top, that immediately proves that in dimension 6, these complete sets of mutually unbiased bases don't work. One reason that we sort of like this conjecture is that most conjectures that we've seen in any case for complete sets of mutually unbiased bases, they often, it's something about non-prime power versus prime power, versus this conjecture is just a blanket statement. Just for any dimension, we conjecture this to be true. I don't know if that makes it easier or harder to prove, but and then I have 15 seconds. So various other open questions relating to just the fundamental theory of these projective toric T designs. We have a lower bound. Is this lower bound tight? Must minimal designs be group designs? This is something that we also conjecture to be true, but we haven't been able to prove. That is, whenever the toric designs are as small as possible, then must they have a group structure? Complete sets of mutually unbiased bases are also conjectured, I think by Zahner again, to be related to affine or projective planes. So there's like a lot of just geometry and mathematics that we think that projective toric T designs might be able to be connected more directly rather than sort of through its other connections. So it's sort of like a big web. We have these asymptotically tight quantum state 2 designs. We think that we might be able to construct asymptotically tight T designs for general T, quantum state T designs. We haven't been able to do it, but we think that it's doable. And this is sort of neat because very little is known, as far as I understand, about quantum state T designs for T larger than 2. And the projective torus sort of gives us a nice, possibly easier, more structured way of trying to study this. And this last one, maybe I actually won't go over. I'm happy to explain if anybody is interested. I think it's sort of a neat thing. We think we are very close. We think we have an idea and we haven't been able to prove it. But if anyone is curious, I'd be very happy to chat. So these are my co-authors. The one on the left is in this room and the other two are not. So thanks for listening. I really appreciate everyone coming.
Thank you very much for the great talk. And any questions or comments?
Sorry, is the mic on? Sorry, I think the mic is not on. Or
okay, so in the case of power dimension, you mentioned that all this maybe correspond to a group projective toric design. So how can you verify this? Because there are many different MUB complete set.
yeah, no. So when I mean that, all the mutually unbiased complete sets of mutually unbiased bases that we've been able to find in the literature correspond to these group designs. We don't have a proof that that has to be the case. We just have, as far as we've been able to find, they all seem to correspond to group designs.
But even for known ones, it seems there are just too many to verify.
Oh, I see. Maybe I can talk to you afterward.
Okay, thanks.
Any other questions or comments? Yeah.
Did you cover the different set part?
Yeah, VT mod M sets and side-on sets.
What did you not cover in here that?
Let's see. What did I not cover? I think I touched on everything actually.
Rigged maybe.
Yeah, I mentioned it in the beginning, but not much.
Thank you for a good talk.
I appreciate it.
Yeah.
Hello. Thanks for the nice talk. Just a quick question. If you could repeat what the relationship was between the projective torus designs and the toric designs and the quantum state designs?
Oh, sure. Yeah, the relationship, I didn't very explicitly state it. The relationship is that if you have any simplex T design and a projective toric T design, you can combine these two to form quantum state T designs. And for T equals 2, simplex 2 designs happen to be sort of easy and nice, and that is fundamentally what lets a lot of this happen. For T larger than 2, not much is known about the simplex T designs. Well, some is known, but I think if we knew a little bit more, then it would help us a lot actually with other quantum state T designs.
Thanks.
Thanks.
the final question.
Thanks for the nice talk. Is there some intuition that you conjecture minimum design is a group design? What the group that you consider, that you have in mind, it should be?
Yeah, no, good question. The intuition, I think the reason we sort of conjectured that is because when t equals 2, the only time we have tight designs, as far as we know, the only time we've constructed tight designs, minimal designs, is for t equals 2, and all those constructions correspond to groups. And we've done not very exhaustive numerics, but some numerics, and those are sort of the only minimal ones that we've found. So that's sort of why we conjectured it. It's not a very strong conjecture. We don't have too much.
The group in this case, Heisenberg wire?
No, sorry. The design itself is just a subgroup of the projective torus. Yeah.
Thank you.
Then, thank you very much for the
Thanks.
nice talk. And thank all speakers in this session. Thank you very much.